Okay, so first, thanks a lot for the invitation, and thanks a lot for organizing actually such an exciting workshop. So I'm really sorry that I did not attend in person. It's possible now actually to travel from Japan, and I think that Taiji actually traveled from Japan, but it was still a little complicated this time, so I preferred to give the talk from here, but I'm enjoying attending all the talks and hope that I can meet you soon in other, like we have other opportunities. So yeah, this talk is about minimum distance estimation, which is an old topic, but I actually think it's interesting to rethink of it. Many papers about robust estimation, bringing more sophisticated methods, but still I think maybe this method was a little overlooked as a way to think about robustness. So I'll try just to explain this actually with basic examples to motivate this and like basic properties of this estimation method in the first part. And then actually in the second part, I will try to focus on one of the distances that actually we studied with this method recently, maximum mean discrepancy, and try to convince you that in some contexts, it is a very useful estimation method. And if I have time in the end, I'll give a word about pseudo-Bayesian method related to this. So I will start with very simple remarks, just like I will consider statistical estimation problem, a simple one, not necessarily in high dimension, but we just have like IID objects in space X, and they are generated from a probability distribution, P naught. And I have a model, a family of probability distribution. Actually, I wrote here, assume P naught equal to some P theta naught in the model. Of course, I will not do that in most of the slides. Maybe we can say actually that we assume that maybe like 2 or 3 slides, and then after that we'll remove this assumption as soon as possible. And the idea is still to try to find a good approximation of P naught in the model, even if actually P naught is not in the model. So obviously what we teach usually to our students is that, well, they can build an estimator, so a function, measurable function of the observations, x1 to xn. And we provide examples like, of course, maximum likelihood estimation. So if the model is dominated, you can define densities and then likelihood, and then actually compute the maximum likelihood estimation. It works well for some models. And actually, we have a beautiful theory about asymptotic optimality, etc., etc. But this is under assumptions. And what I will be interested in now is mostly when these assumptions, what happens when these assumptions fail. So I will present a few examples, actually very simple. These examples was taught to me like when I was following Lucien Berger, actually lecture during my master degree. But just a simple remark, if you use this translation model with a density that is infinite at 0, then actually the likelihood will be infinite at each point of your data set and will not provide any thing like its maximization will not define an estimator, and it does not seem to lead to anything about possible estimation of theta. While actually it's very simple to do estimation in this model. Actually, it's not heavy-tailed at all, and you can use just a simple empirical mean. But MLE in this case doesn't work. Another thing, actually, I'll be interested in this talk is also to have something that will not fail in the case of misspecification. And very simple remark, like possible model for contamination of data is Hubert's contamination model. So in this case, you think of the model as almost well specified, actually, with large probability, but with small probability, the samples are drawn from another probability distribution, which can be absolutely anything. And then here again, it's possible to make MLE fail quite easily. For example, if you're estimating the upper bound of the uniform distribution with MLE, then actually the MLE is the maximum of the X size. But if Q is any distribution that can go outside of the support, then MLE can be very, very far actually from the correct theta naught. Well, actually, it will be possible to design estimation method that can still recover theta naught in this context. Okay, so in the beginning, actually, this project started just by trying to define very simple estimators, but that would be like robust to this kind of misspecification, even to more severe misspecification, like adversarial, contamination, adversarial contamination. And also estimators that would not require assumptions on the likelihood and would be able to deal actually with such examples. It started a little as a game, actually. Try to write the convergence results with the fewest assumptions possible. But then hopefully I hope to convince you that in some cases, it's actually quite competitive and works well in practice. So the idea is very basic. You define, as usual, the empirical probability distribution, 1/n times the sum of the Dirac masses at each xi. And then you minimize, you fix a distance on probability distribution, and you minimize the distance between Pn at and P theta for theta in the model. Okay, so this was discussed actually as a general estimation method in a very old paper. But interestingly, this idea has been mentioned very often, actually recurringly in the literature as a way to produce robust estimators if you choose the distance d well. So actually, this is now what I will try to detail a little. So in particular, there was this paper by Peter Bickel, is very beautiful and very famous actually on robustness. But at the end of the paper, the discussion contains also many interesting remarks, and there is a discussion by Stuart Holm actually, where he provides a few examples of distances that leads to robust estimation. So today I will focus mostly on these type of distances, integral probability metrics, well, semimetrics in general, but actually I will focus to the metric case. So the distance between two distributions P and Q is defined as the maximum discrepancy between the expectation under under P of f of x and the expectation under Q of f of x when f is any possible function in a family f. Okay, so if f is well chosen, this is actually a metric, and I will discuss that actually in the example we will discuss later. And of course, also there are assumptions on the family f such that, of course, this distance is finite, but all this actually will be discussed when I will come to specific examples. So essentially, what is nice with that is that all the theories that was developed for learning, machine learning, actually in the past 10, 20, 30 years, gives immediately tools to understand when minimum distance estimation will be consistent if you use it with integral probability metrics. It's almost direct, actually. The proof is just like 2 or 3 lines just to write things properly, but you have this result saying that if the xi's are IID from P naughts, and if you work with, say, a bounded class, so I will bound it by 1, and then of course, like actually, if it's not 1, you can just like rescale everything. Then actually, the expectation of the distance between P theta at and P naught is the smallest possible one. Okay, the infimum, the distance of P naught to the model. Plus simply a constant times the Rademacher complexity of the family F. Okay, so in some sense, if you know that if you have if you use an integral probability metric with family F that has a Rademacher complexity that goes to 0, then you will have a consistent estimation with MDE. So just a reminder, but I assume I know that actually here in the room everyone is familiar with this, but just in case I remind the definition of Rademacher complexity. So essentially you have here a mean of epsilon i's that are signed random variables called Rademacher random variables +1 or -1 with probability 1/2. And without the sub here, actually this quantity would of course have a mean equal to 0 and converge actually to 0 by the law of large number. But of course, like taking the supremum over rich family F, you can actually find a class, a function f that will interpolate the epsilon i's, and if the family becomes richer and richer, this can be actually can remain constant when n tends to infinity. So I will provide examples. This one is not something that we will use. I will use in practice actually in the talk, but it's more maybe like a kind of to understand in what situation this works or not. So if I consider indicator functions, then actually it appears that in this case, classification theory tools that were developed and using classification theory can be plugged here and actually tell you that essentially what you want is the Vapnik-Chervonenkis dimension of the family F to be bounded. So actually it's known that, for example, I provide this reference of the paper by Bartlett and Mendelssohn, that actually the Rademacher, if the Vapnik-Chervonenkis dimension of F is bounded, then actually you have this bond on the Rademacher complexity, and you just have to plug this into the previous inequality here, sorry, to obtain that actually you have a method that will be square root n consistent in distance df. Okay, so that's an example where actually you have a criterion to know whether your distance will, I mean, minimum distance estimation will lead to consistent estimation or not. Actually, there are maybe like, yeah, just in order to make things a little more concrete. So you could consider, for example, the set of all measurable sets, then actually your minimum distance becomes the total variation distance. And then actually, usually, unless the object space is finite, otherwise the Vapnik-Chervonenkis dimension is infinite and the Rademacher complexity does not go to 0. So it's not a suitable example in this case. But for example, you have like, of course, if you just, you work on R and you just take half lines, then you obtain the Kolmogorov-Smirnov distance. And actually, it was historically one of the examples proposed in the discussion on the paper by Sturr-Holmes I mentioned before. And in this case, actually, the Vapnik dimension is 1. So it means that, for example, in this case, you recover a very simple results, which tells you that actually your estimator is consistent when the model is well specified, and otherwise it still targets the best approximation of the model in the model of the true probability distribution. This is not an example I will work on like later in this talk. So I will now come to the MMD distance, which was studied a lot actually in the past 3 or 4 years in this context of minimum distance estimation. So if you consider RKHS corresponding to a kernel K of xi, and so K actually is phi of the scalar product between phi of x and phi of y, where phi is a non-linear map between, or possibly linear, but like a general map between the object space and the RKHS H actually. Then it appears that if your function phi is bounded, which actually leads to the kernel K being bounded, then actually you can define the expectation of phi for any distribution P, sorry, on X. And actually for characteristic kernels, the property of kernels to be characteristic exactly actually ensures that this map is 1-to-1. So then actually what it tells you is that the integral probability semimetric is a metric in this case. And in case you're wondering about these properties, it appears that actually the most popular kernel, like the Gaussian kernel, satisfies these two properties. Okay, it's two properties. It's bounded by 1 and it's characteristic. So in this case, actually, the integral probability matrix can be rewritten as simply actually a norm in the Hilbert space, the norm between the expectation under P and the expectation under Q. And the fact that actually it's a norm in the Hilbert space, so when you square it, you just have like actually easy computations. And I will come back to this in the second part. It's what motivated actually the use of this distance a lot actually in this context. But for now, I will come back. I will stay just on the basic theoretical properties. It appears that actually the Rademacher complexity in this case is is bounded by square root of the supremum of the kernel over n. So when the kernel is bounded, actually it's just square root of 1 over n. And to be honest, it's a little unnecessary in this case to invoke this theory. You can just like use this representation of the MMD, and it just actually, in this case, the result I presented before, you don't have to use the Rademacher complexity. It's just the computation of a variance, but in the Hilbert space. And in this case, the result is super simple, and it tells you that if you choose your kernel well, you don't have to have any assumptions on your model or on p-naughts, and you always have consistency of this estimator. Okay, so we have recently, like with my former PhD student, Badreddin Sharif Abdelatif, I show a photo of him actually when he was visiting in Japan, just before it became impossible. Then actually this paper, of course, like it's not just the proof of this formula. We have many results related to robustness and also extensions to non-IAD setting. I will not cover today actually, but I just want to mention this in case you're interested in the robustness properties. And actually we dig on these properties in this paper. Another example, I feel less comfortable with, in the sense that I know that there are many specialists of optimal transport and methods related to Wasserstein distance publishing on this topic, and I don't. So actually I don't know this example that well, but I want to mention that it also corresponds to, of course, to integral probability metric, is the Wasserstein distance, where actually you take the supremum over Lipschitz functions. So it appears that actually in general, it might always not be a good idea, because if the functions are not, if the space is not bounded, you can still actually have situations where actually you cannot prove that the Rademacher complexity goes to 0. On the other hand, what you can do is actually, for example, if you work on a bounded space X, then you can do this, like have kind of similar to Rademacher complexity going to 0, and then deduce the proof of the consistency of the minimum distance estimation. So I read actually a paper by Francis. We cite it, but it's not cited in the slides, but we cite it in the paper, where actually you prove such concentration results corresponding to the Wasserstein distance. So actually then there were papers on estimation with this Wasserstein distance based on this kind of results. Then actually, in order to connect it to robustness, I will not enter detail too much, but just a very simple observation is that actually if, well, I just come back to the very standard result and just think here we use the MMD, or we use something simple like Kolmogorov-Smirnov. So the Rademacher will be in 1 over square root of n. What does this tell you about robustness? And it appears that these results can be plugged immediately in the context of, for example, Huber's contamination model. So if P naught is actually 1 minus epsilon times P theta naught plus epsilon times some probability Q, actually just using rearranging terms in the definition of the integral probability metric, and then using the triangle inequality, you see here that in the end, on the condition that the class of functions that you use in the minimum distance in the metric is bounded by 1, then actually the distance between P theta naught and P naught will be smaller than a constant times epsilon, which means that here, if you are in Huber's contamination model, you will actually, the distance between P theta at and P theta naught will be bounded first by like the Rademacher complexity, which gives the rate of convergence, and by epsilon, which is actually the distance to the truth. So you can then actually, we're working a little to connect the distance corresponding to F to the distance corresponding to parameters. You can deduce rate of convergence and recover in some situation optimal rates of convergence with respect to epsilon n to n actually on theta at. Actually, I just described here Huber contamination model because I think that it's very easily understandable from the initial results how you obtain the robustness in this case. But actually, it works exactly in a similar way in adversarial contamination. In this case, actually, adversarial contamination is not more complicated due actually to the boundedness of the function in the class F. So you would have exactly the same result if you replace Huber contamination by adversarial contamination. And this is just a very toyish example. We did not include this simple example in the paper, but just to convince you actually. Like I compared MMD with Gaussian kernel and KS and like minimum distance estimation based on these distances to the maximum likelihood estimator for a Gaussian model where you estimate the mean. So sorry, this is something super simple. For now, we just estimate a mean of a Gaussian in dimension 1, and we know the variance. But just like as an example, if you replace like 2% of the observations from the truth by a Cauchy, and you see that, of course, MLE does not work anymore in this case, but MMD and Kolmogorov-Smirnov distance estimation remains good, actually. And here, kind of more, maybe less kind of Huber's type, but more like adversarial type. I know what is worst thing for the mean in dimension 1 is to pull one observation to infinity. And by doing so, still you have very good performances for MMD and KS, but not for obviously for the empirical mean. So this is a very, I know this is a toy example that's not maybe the most exciting. And obviously here in this case, you don't have to use such a theory. Actually, you could just replace the empirical mean by the empirical variance and you would recover the same results. Now, actually, I will provide a few examples of more sophisticated situations where actually using the MMD turned out to give very good results. And maybe I will try to explain why it became a little more popular than other examples. I'm also, I just like, I will propose here 4 examples, and 2 of these examples come from my papers, but the workshop is also about deep learning and differential equations, and I have not worked on this topic related to MMD. So I will also give pointers to 2 exciting examples by other authors, citing them, of course. But I hope you will not like. It's just like a kind of advertisement, maybe to explain you that this method can be used in more sophisticated models. So I hope you will not find it too superficial. But first, actually, just a few computational considerations. Why is this MMD distance so convenient? So just remind you the definition, and then actually just 2-line derivation. You do the optimization in H actually, and it turns out that this can be written as a norm actually in a Hilbert space. So if now you use the definition of the kernel in terms of, or the representation of the kernel in terms of scalar product with respect to the map phi here in the first line of this slide, then actually just in 2 lines you get this expression for the squared MMD between p theta and p n hat. So you have like p theta squared minus the cross product plus p n hat squared. Okay, like it's just expanding a minus b squared. But what's interesting here is that actually, first, the third term, okay, you have n squared terms, but on the other hand, it does not depend on theta. So when you want to minimize this with respect to theta, you just like can ignore it. And then the first 2 terms, I don't say that it's a miracle. Like it's, of course, these terms can be computationally difficult, but on the other hand, what's nice is that they only require you to be able to compute expectation with respect to the model p theta. There is absolutely no expectation with respect to the truth p naught. So as long as your model is something you can deal with, then actually it should be feasible. And if you cannot compute this, you can compute this integral explicitly in some cases, but even if you can't, then actually in some cases you can still use Monte Carlo. And the only condition that you have to be able to use Monte Carlo methods on this is that you are able to sample from p theta, which means essentially that you have a generative model. If you have a little more than that, if you have a dominated model and you can define a likelihood, then actually it's also possible to provide a formula for the gradient of the MMD with respect to theta. And whatever this formula is, what's interesting is that here again, the gradient is an expectation with respect to p theta, which means that by sampling from p theta, you can build an unbiased estimation of the gradient. Under very weak conditions, when the kernel is bounded, this will be like strongly concentrated. So you have good estimate of the gradient, and you can use stochastic gradient method to minimize this. Okay, so first example, historically, actually, that's interesting. Like people designed this method. I think that the first time they used it in practice, it was for very sophisticated model. Before maybe that actually we realized that it could be used also for very simple things. It was used in a series of papers in 2015 to train adversarial networks. So like adversarial, to train generative network. So you want to be to learn to simulate images or videos to maybe to do something better than to propagate fake news, but still like it has other applications. And then actually what you do is that you sample from a uniform distribution, and then you pass your sample through a map. Okay, and this map will actually be a neural network with some weights, and you will obtain an image as an output. And then actually you want to train the weight in a way that the distribution of the output will match exactly the, or as much as possible, the empirical distribution of a data set that you have. Just an example of this actually here. If you sample from the model, you want that actually your p theta in the end matches p n hat. So in this case, you don't have a formula actually because you don't know p theta density, but actually using automatic differentiation tools, two papers were able to minimize the MMD to learn theta and to produce what was probably good at that time. It's already 7 years ago. So now there's a huge improvement, of course, on generative networks. And I think that MMD became, on this topic, less popular than Wasserstein later, but still they were able to actually to train sophisticated model using this distance. And to produce actually some images that were not in the dataset, etc. A second example from another paper. So this paper is actually also like super nice on MMD and provides like the part of the theory that I did not derive today. That is the asymptotic theory when the estimator is asymptotically Gaussian and how is its asymptotic variance, etc. They proposed as an example a stochastic differential equation and estimation of the corresponding parameters actually. So here the idea is that you have a small dimension parameter, but the objects that you observe are a little complex. Still, it's quite easy to sample if you know the function b. If you had some parameters θ1 and θ2, it's easy to sample from it. So in the end, they used the MMD criterion with the gradient, stochastic gradient descent actually to optimize it. So they have an example in the paper on a stochastic Lotka-Volterra model. You have here examples of trajectories, and then actually they corrupted the trajectories with some observations that were not coming from the model. And in the end, they used both MMD and Wasserstein actually, and had, you see, results. So for both methods, you can see that when you have like 0, 10, 20, 30, even like 40% of contaminated observation, you still have convergence to something that is very close to the true value of the parameter. So, sorry, I think I spent enough time to advertise for other people's work, so I will come back to our paper. We have also two applications of this. I will be very brief on this one and spend a little more time on the other, but we studied regression in this context. Just want to point out that here, finally, at this point, the theory stops being simple in the sense that, like until now, I described how to estimate a parameter, not how to estimate, how to estimate a distribution, not how to estimate a conditional distribution. And it turns out that, of course, there is natural ID. You can say, I can estimate the distribution of X and Y. Well, I estimate the distribution of X by the empirical distribution. And then I try to estimate the distribution of Y given X using MMD. It turns out that if you do this and you use the previous theory, what you can show immediately is that actually you estimate the distribution of the pair X and Y consistently, but it does not correspond to the regression objective. And in some sense, if you want to switch to the more usual kind of things we want to say about regression, that is the estimate that we estimate correctly the distribution of Y given X, then it becomes more difficult. And at that time, the beautiful no assumptions at all collapse, essentially because when you integrate the results with respect to X, you will have the question, like essentially if you define a kernel in the space X, Y, X times Y, then actually if you integrate such a function with respect to X, will you obtain like a function with respect to Y, which belongs to a corresponding RKHS corresponding to a kernel in Y? And this question is actually, it doesn't work all the time. So at least you have to define a kernel that will be designed for the model you are considering currently. We were able to propose many examples, and it's in a paper actually submitted with Mathieu Gerbert from Bristol, sorry. But then actually, it becomes immediately more technical. And I think that there are interesting questions actually to solve with respect to the kernels that, will work in this context. Another example, and I think it's the case where actually probably the method was the most, how can I say, bring something new with respect to what people were doing already in the field, was copula. So actually the problem is that in copula, you have many models where actually you don't have alternatives to MLE. Robustness, of course, remains an issue. And then actually they have a pair of models that are even not dominated. So you cannot define likelihood, for example, Marshall-Olkin copula. But we wrote also a paper on this topic in the end, copula with MMD. We have an R package corresponding to it. And essentially, in this case, I would say that like the paper contains like these non-asymptotic results and the asymptotic derivations. But what is nice is that, for example, the Marshall-Olkin copula family, where all the estimators until now were very ad hoc and just defined for this family. So you don't have the MLE in this family. It's not dominated, but it's not a problem. You can use easily MMD estimation, especially as it's quite easy to sample from copula models. And in the end, it gives results that are very competitive to all other methods. So like whether we use like here, so it's a Gaussian estimation of a Gaussian copula. And we have like on the left panel, it's more like Uber type contamination. So in this case, the blue one here is the one of the version of the MMD, and you see that it's less good than the red one that is the MLE when there is no contamination, which is okay, fine. MLE is asymptotically efficient, and it's not the case of MMD. Actually, we have a small gap in the variance. But then as soon as you have a little contamination, then it's the opposite, of course, like MMD is more robust. Now with, we defined kind of contamination that were meant to really make the landscape of all the criterion change a lot with respect to like changing the likelihood a lot. So it's a kind of adversarial contamination. And in this case, the MLE is destroyed. Like you cannot even see actually the risk of the MMD estimator in this graph. And that's for Gaussian examples, but we did it for like Clayton, Copula, Gumbel, Frank. We have actually a few simulations for the Marshall-Olkin copula for which you don't have a likelihood. So actually you don't even have the MLE as a competitor in this case. And in each case, it works quite well, actually. I'm sorry, but I cannot remember at what time I started and at what time I am supposed to stop. So can I just ask you how much I have left?
You have 10 minutes, including questions.
Okay, so that's, I'm reaching part 3 and it's quite short, actually. So it should be fine. Just want to provide a glimpse on Bayesian methods using MDE, because actually for the above, for the reasons I mentioned before, actually robustness There were also like a few papers on pseudo Bayesian methods trying to replace likelihood by distances that would lead to more robustness. One idea that I will just mention is to use like kind of generalized posterior. So you replace here the log likelihood by discrepancy function, and it can be of course, like this idea is popular in pack-based in many fields, and these posteriors have been studied in many contexts. In particular, when Rn is actually MMD distance, we also like derived a few properties and did a few simulations in a paper with Badreddin. And in the end, it's also feasible to do computation via variational approximations and to derive actually also properties on these variational approximations. Now, I skip this part actually a little. You can like read the paper if you're interested in. There was also a paper I wanted to mention. Actually, I just became aware of it like in the past days, but there is like also asymptotic study, because our paper just mentioned like kind of non-asymptotic bounds, but you have asymptotic study, and Bernstein von Mises results for this kind of pseudo Bayesian methods. But I think that another of course like natural algorithm in this context is ABC, in the sense that ABC, as the algorithm I mentioned before, actually that would be like gradient optimization of MMD, only require you to be able to sample from the model. And in this case, it's quite actually natural to propose the following. So you just say like sorry, first I remind like just the general ABC algorithm, where actually you have a sample and model. And so the idea is that you have a prior pi, sorry, and you sample theta from the prior, and you will accept it only if it's able to, if p theta generates samples y1 to yn that are similar enough to x1 to xn. So actually, it's known that if you are in the finite, if you use like a kind of, sorry, discrete set for x, so actually you have the probability that the sample x1 to xn that is equal to the sample y1 to yn is not equal to 0. And then actually, if you accept only when you have equality, then actually you sample exactly from the posterior. Of course, the probability of this is too small in general, and actually even it's null if you have like continuous variables. But then approximate version of this algorithm, where instead you accept theta, you keep theta, only the distance, a kind of distance criterion between x and y is smaller than epsilon, produces theta. Well, it produces theta, but in some cases, actually, it's possible to prove that it's not that, it produces theta that is not that far from being sampled from the true posterior. So this is actually an important question. And in this case, actually, we studied the idea, say, well, instead of doing like ad hoc distance here between x and y, why not compare actually the MMD distribution, or actually any the MMD distance or any other distance? So that's actually what we did here. So actually, sorry, I don't think I wrote, yeah, actually it's here, sorry. ABC with IPS. So in this case, actually, the distance between P and Q that we consider in the previous algorithm is the integral probability matrix. And so the algorithm, sorry, it's maybe too much lines in the slide, but it's just the same as the previous one, actually, apart from the fact that in the end, I will accept theta only if it produces a sample y1 to yn, such that the empirical distribution of y is close to the empirical distribution of x in the sense of the corresponding integral probability matrix. I will denote with this super heavy and ugly notation the corresponding posterior, but sorry, I want to keep in mind that it depends on n, on epsilon, and on the integral probability metric f. And the question is, does this look like the true posterior, or actually maybe even better, does it work better than the true posterior, which actually can be the case. So we are currently finalizing a paper. So again, it's written, we're just rereading it, and it should be archived by the end of the week, or maybe next week, hopefully, with Sergio Legarmanti and Daniele Durante. And we studied 3 questions actually related to these pseudo posteriors. Like essentially, it's true that if epsilon tends to 0, you recover something that is not very far actually from the correct posterior. But interestingly, also, we have like kind of contraction of the posterior results. So it's not the true posterior, but contraction of these approximate posterior results. And if epsilon n is well chosen, actually you will keep the robustness properties that we had actually in the non-Bayesian case. So the result is as follows. So essentially, the assumptions are the same as before. We want to have, we need to choose to work with a class F that has a Rademacher complexity that goes to 0, and we need to have this function bounded. But like, once again, the example I have in mind now is MMD with kernel that is Gaussian. And then actually you have one additional thing is this prior mask condition, but it's quite standard. I mean, like even if I was working with a usual posterior and not with this kind of approximate posteriors, you would have the same kind of assumption to be able to provide a rate of contraction for the posterior. And then in the end, you obtain that essentially your parameter theta either will contract to the truth if the truth is in the model with a rate essentially 1/√n up to a few log terms, or at least if the truth is not in the model, you will stay in a radius corresponding actually to the distance that is the best approximation, the distance of the truth to the model. Okay, so essentially you recover as can be expected, maybe the good properties from the frequentist approach. So that's it. I'm learning how to insert Japanese in my slides. So that just means that it's the end, and that I thank you very much. Thank you.